Good morning, everyone, and welcome to the IBM Quantum Seminar Series. I'm your host, Zlatko Minev, tuning in from New York City today. Let us know in the chat where you are coming in from yourselves. And I have the pleasure to be back and to welcome you to 150, 160 episode number. Paul will tell me in a second, dedicated to you, the research and academic quantum communities. Now, in just a minute, I'll be thrilled to roll out this week's episode with Anushya Chandran from Boston University. We had a really great summer school that Anushya helped organize, and maybe she can tell us a little bit about that, which was on many-body systems at Boulder. It's a very long, famous story. So that's kind of the origin of this series. And before we get there, I'm so glad that you joined us on time. I see many of you already replying. Where are you tuning in from in the comment chat box on YouTube? If you haven't done that yet, please do. That's the same place where you can ask questions of Anushya and myself during the live stream. And today I see we have folks from New York City, from Paris, from San Diego, Dallas, UK, Yokohama. I see Paul is telling me this is episode 154. We have folks from London. So thank you, everyone, for making all the different time zones to Michigan, Toronto, Bogota. It's really always a pleasure to see that. Without further ado, let's get to it. This seminar takes place every Friday at noon Eastern Time. You can always go back and rewatch it, but you can only ask questions live now at noon time. Today, it's my pleasure to introduce you to Anushya Chandran from Boston University. And hello, Anushya. How are you today?
I'm good, Zlatko. Thanks for having me.
It's my pleasure. Where are you tuning in from today?
From my office at Boston University, so Boston.
All right. Well, we'll be sure to visit sometime. Before we turn over the screen to you, allow me to share your bio. Anushya Chandran is a many-body condensed matter physicist at Boston University. Anushya obtained her BTech degree from the Indian Institute of Technology in Madras in electrical engineering, and later your PhD from Princeton University in physics. After a postdoc position at the Perimeter, Anushya moved over to Boston, where she is still presently today as an associate professor. And Anushya, of course, is the recipient of many awards, including the Sloan Fellowship, the Career from the NSF Fellowship. I won't name all of them. We'll just cut it there. And I think with that, Anushya, the stage is yours.
Great. Thank you very much, Zlatko, for the kind introduction and an invitation to give this seminar. Hello, everybody. Those were a lot of places across the world. Yeah, that's very impressive. Just so many people get together at the same time every week. So I'm here to present a story, actually a relatively short story. So please interrupt me with questions at any point. I heard that is the format anyways, but my talk is also relatively short, so I should have plenty of time for discussion. So what I want to tell you about today is about efficient local classical shadows with number conservation. Zlatko just told me that for, I suppose, not exactly planned reasons, there have been several talks on classical shadows in recent history. So maybe that's a good thing, because maybe you've heard some of it before in the introduction, but maybe this also builds on other things you've heard. So this is work with Sumner Hurth, who is a graduate student here at BU, Michael Flynn, a former postdoc here at BU, and Chris Lauman, who's my colleague down the corridor. And this, to references, this later archive one is the relevant one for this talk. So let's get cracking. Of course, that's what motivates this seminar as well, the recent re-interest in all things quantum. And this is really fueled by the new hardware that experimentalists across the world are able to create in a variety of physical platforms. So I have some up here, closest to the heart of probably a good fraction of this audience are the superconducting qubits that, say, IBM is building a quantum computing platform based off. So these platforms boast an increasing number of qubits with increasing coherent control, and are able to do several remarkable things already. So one such thing is, to make interesting states rho, starting from simple states of your qubits, say the ground states of all of them, through some circuits. And so we are in the NISQ era, where in several of these platforms, the exact number of these qubits and the depth of these circuits are all being pushed. The fact that we're able to do this has already been a blessing, in part because Hilbert space is a big place, and it is the fact that it is a bigger place in the quantum cases compared to the classical case is why we want to build a machine that is based off the principles of quantum mechanics to make new states rho in Hilbert space that are impossible classically, or don't exist classically, and thus do interesting things with them. Right, but what is a blessing is also a curse. Hilbert space is a big place, so these sources of noise I have up here, right, and NISQ, I'm sure, is a word everybody's heard here before. It, the N there is noisy, and so the same. Although this hardware is quite programmable, the fact that we have noise means that we can get lost in this big space that is Hilbert space, and so it's very important that one characterizes the kinds of states that one makes. This process, however, is very expensive and goes by the name of full quantum state tomography to really know what state you have created in this big space that is Hilbert space. And the goal of full quantum state tomography is to characterize whatever you've made through your hardware through repeated measurements. So what it looks like at a high level is something often like this. So you through whatever sequence of operations you make some state rho of interest to you, and this is of V qubits. And now there's a unitary U, a giant unitary U that you might act here, and then you make a bunch of measurements, and you do this again and again and again. The reason to dunk this giant unitary U here is to allow for measurements in different bases, right? Because in the end, you maybe often what you're doing are measurements of simply is every qubit in the excited state or the ground state, but you want to measure in conjugate bases to that, and so you do that using this unitary. Okay, so you do this again and again and again and again, and then you have some reconstruction procedure to figure out what the full state rho was on the left. And this is, as you might guess, very expensive for lots of reasons. So rho in general is a density matrix of your state of V qubits. V qubits have 2 to the V states. And so when you're trying to characterize a giant matrix that's 2 to the V by 2 to the V, it has exponential and volume numbers in it in the first place. So definitely you're going to need exponential and volume measurements. And of course, to store such a giant matrix, you're going to need similarly exponential scaling in the volume, classical resources, right? So this gets prohibitively hard as this number V goes up. And I don't know what the exact record is, but I think full state tomography is maybe done for something like 10 qubits before. And 2 to the 10 is 1024 already. It's just getting worse and worse. Okay. So that seems like a really hard problem. Nevertheless, we'd like to understand our state rho. So what do we do? And so here we realize that, at least as physicists, we are often only interested in physical properties of rho. So what we would like is a description that lets us measure and predict the physical observables. So for examples, you would want to reconstruct correctly through your measurements all the expectation values of any operator with k acting on k qubits at the same time. Okay, so something like this, you'd want to be able to reconstruct from your measurements, and you'd like to do, not just do this for a single O, a particular type of O, but for classes of them, which are interesting, right? So they might be interesting for different reasons. So perhaps there is some kind of exotic order in your state, which you would want to characterize through some string operator that involves a string of these acting on a string of qubits. or maybe it's correlation functions telling you how distant qubits affect one another. Maybe it's just the energy of the system. Maybe you're in the business of trying to solve for the trying to find an exact eigenstate or get close to an eigenstate of a given Hamiltonian, and you want to know what did you do that and what was the variance, etc. Right? So there's large classes that are independent of the state rho that you would be interested in measuring. And classical shadow tomography attempts to do this without trying to fully reconstruct rho. So the goal is to create an efficient classical description of rho to predict classes of observables. So again, not the entire state, but large classes. The recent spate of activity on it traces back to Scott Aronson's work in 2018. And I have some of the references here. I think the one that maybe set off a lot of recent work is this one from Huang et al. From Press Skills Group in 2020. And so just to emphasize up front, there's always this delicate balance. When you say you want to predict classes of observables, at some point, it just makes sense to design an experiment to measure the particular observable of interest, right? So tomography doesn't want to do that. You still want to be agnostic to the exact observable you reconstruct. So you want to create a description still of the state. And so, which is to say, you want to keep this philosophy of measure first, ask questions later. The questions are the observables of interest. But biased by the fact that your description will be more useful for certain classes of observables as compared to others, which is to say the error bars with which you can estimate the observables is controlled for certain classes and maybe larger for others. Okay, so it's still trying to do tomography, not just measure specific observables. Okay, but it wants to do it efficiently, not paying these exponential costs in the volume or the number of qubits in your system. A scheme that is very efficient and the 2020 paper from Huang and co-authors really fleshed out and showed its power off is this product scheme. So I'll go over what it is and that'll set the stage for what we've done as well. So on the left here is once again a state of interest that we would like to characterize. And to do this characterization, what we do is we act on each qubit independently a single qubit unitary. This is drawn randomly from some gate set. So there's many choices. One that works is, for example, the identity. So do nothing, apply the Hadamard gate, or apply the phase gate, each with equal probability. All right, so you do that, and then you measure. Measure in the Z basis, asking if you have a qubit in the excited state or in the ground state. And you build a table known as the shadow table, in which you do this again and again and again. So rap 1 to rap m is the number of times you repeat this experiment, each time drawing a different set of these single qubit unitaries independently on each site and independently of all your previous attempts, and making these measurements and getting a shot, some snapshot of your system. Okay, so great. You've done this characterization step. Now, of course, the question in front of the house is how are you going to reconstruct the state from this? And so the protocol that you have done defines what's known as a shadow channel. So it in goes your state rho. This process that you have done can be described as a channel, whose output is the expected value of your post-measurement state. Okay, so hopefully that makes sense. So that you can treat the entire process that you did that built this table up as a channel that takes in your state and spits out something else that depends on rho. And why is this a useful way to think about it? It's because if you can model this as a channel and you can get some control over what this channel is, and if it's invertible, then you can build you have a formal relation telling you what rho is. So it's this thing out here in which you've applied this M inverse on this object that you've got on the right. I'll just make this operational in a second. So for what this gives you, these two manipulations, is it gives you an unbiased estimator which you can reconstruct from this table. So let's maybe just go through this expression to say what that means. So from this sequence of table entries, you build this state. So this would be your post-measurement state. So B's are the up-down measurements that you obtained, and you undo the unitary that you did on your state before you made those measurements. You do U dagger and U on one side, and then you take each one of these states from every one of these rows and pass it through this M inverse channel, and then you sum these things up, and that gives you an estimate for the state row. That's what you get from doing these kind of formal manipulations, right? So this object is easy to construct. All the details are hiding in what it means to apply this M inverse on each of these states that you build from the entries of your table. Okay, so if you have an unbiased estimator for your state, you also get unbiased estimators for observables. So this is the expectation value of O, and we've just done a little bit of rearranging to make it seem like what you need to do is in each of these, for each of these entries of your table, you build this state undoing the effect of the unitaries that you acted, and now you act this M inverse channel on the operator O. Okay, so it's and so that again gives you a way to take every row of this table and get an estimate of the expectation value of trace O row. Okay, so this is fine. This is seems like some general purpose scheme. So where is all the complexity hiding, right? So it's hiding in several places. And so we can ask several questions. So how many samples does it take for you to get the expectation value of O with some error? So that's this M here. How many entries in this table do you need to be able to reconstruct this expectation value with some precision? That's one question. Next is, of course, how hard was it to do these unitaries? How hard was it to sample them? How hard was it to implement them in the when you were trying to build these rows of the table? And then, of course, what are the classical resources to compute all the stuff in the middle there? It's fine, we wrote down this table, but then we have these expressions that we are computing classically, specifically this M inverse acting on O is a classical post-processing step. How hard is it to do that? And in particular, what resources are needed and how does that scale with the number of qubits? Okay, so the product scheme that we described is very efficient in all these kinds of complexities, which is why I think it made such a big splash a couple of years ago. And so let's go through this table and talk through each of these pieces. So once again, what we are asking about is we're asking about the resources needed to reconstruct expectation values of operators, where the operators are all possible k-body Pauli strings. Okay, so that's so we said again, shadow tomography attempts to to reconstruct classes of observables. So this here is our class. So what do we need? This product channel. While we looked in the pictures, made this clear already. We need to be able to do single body gates, and we need to do single body measurements, and as many as the number of qubits that we have. Okay, so that seems all right. No exponential scalings there. Sample complexity. So sample complexity is the number of entries of the row that we need to guarantee a given error on our expectation value. So here we see that it scales exponentially with the bodiness of our operator. That's as expected. Observables that involve more qubits are harder to reconstruct in that one needs to do more repeated such measurements or have more entries in our shadow table to bring down the error to a given value. But importantly, you notice that this is independent of the volume of the system. So that's good news, right? So if you say, I have, as you scale up the number of qubits in the hardware, as people are constantly doing, if you were always only interested in saying, okay, that's great, I have 200 qubits today, I'm still only interested in all 3-body observables, the number of entries in the table that you need is not scaling up with the total number of qubits. So that's great.
And Anushya, can you clarify for us, when you say k-body Pauli strings, do you mean k-body local, or can they be spread out, non-local?
Oh yeah, sorry, k-body no locality in them in the sense of where they are in space.
Okay, purely the weight.
Yeah, only the weight. Yeah.
Great. And go ahead. Maybe there was one question, but maybe you'll get to it in a second about how is M, the curly M, built out from the shadow table. But I have a feeling you're going to come back to this.
I'll, actually, I'm not going to say it in detail. Oh, how about this? I will present kind of what we do for hours, and then maybe I can say more again about how it's
Okay.
done.
So
Yeah.
Deepak, if we don't answer it by the end, just circle back with your question.
Okay, should I keep going, Slavko?
Yes.
Yeah.
And maybe just remind us what V was.
Yes, V is the number of qubits. V, maybe physicist notation, I always think V for volume. So V is number of qubits.
Okay, thank you.
Yeah. So, all right, so that was sample complexity. Now storage per query, how much each element of that row, how our resource is scaling. Well, that's just V, right? We just store V, number of qubits, worth of information for which unity did you apply, what outcome did you get. So that's very efficient. This is where all the action is, of course. Well, one place where a bunch of the action is. Post-processing per query. This is, so I guess in response to Deepak, I didn't tell you how to do the M inverse, but what this is telling you, though, is whatever we're doing, it's very efficient, because applying that M inverse to the operator O only needs kind of resources scaling with K, the weight of the operator string. So it's very efficient. So yeah, punchline, if you didn't follow all that, is simply there's no exponentials in the number of qubits, or V, volume of the system, anywhere here, which is great news. It's exactly what we were after for trying to step away from full state characterization and instead bias ourselves to better characterize these classes of observables. Okay, excellent. So that's the background, and it's really taken off. I'm not giving by any means a survey of the field. People have explored. People have actually tried this on in several platforms, and two, they've explored all kinds of generalizations and all various axes, effects of noise, effects of different statistics of your particles, etc. But so the thing I want to talk about today was actually motivated by an open question in the field, at least as of last year, which got us thinking, which is how does all this work if we had number conservation? And of course, you could say, why do you care? And the direct reason to care is applying these kinds of shadow tomography techniques to atomic systems, where right. So these are this is a cartoon showing you a lattice. This is an optical lattice, so a lattice of light intensity, and the blue balls are a cartoon of atoms in them. But the point being that atoms are conserved in the sense that you cannot do any operation acting locally which creates a superposition of atom and no atom. There's no coherent superposition of that's possible. Yes, you can lose atoms, but that creates mixtures of states with different atom numbers, right? So it's a fundamental conservation law, and something that you can't get away from. And maybe a priori may seem like, oh, so what? Maybe just go do the same scheme. Maybe it works out. And at least we pause for a minute, because what the product scheme, which relied on single set unitaries, can be trivial. So in the sense that, let's think about hardcore bosons. Hardcore bosons means that you can have no atoms on a site or a single atom on a site, at most one atom per set. And so then because we cannot form superpositions of atom being there and not atom being there on each site, your unitaries on each side are just at most give you a phase. They don't do anything to the atom occupation number, and so the scheme will certainly fail as is. Because you're unable to rotate and make measurements in different bases. Okay, so
a quick question before I let you get too far. If you go back one slide before this, there's this sample complexity of 3 to the k, which for people who have done traditional tomography reminds you a lot of, if you have, well, I guess it's a little, maybe this is differences. If you have n qubits and you kind of want to cover all Pauli terms, I think you need to cover something like 3 to the n, because for each qubit you either measure in the x, y, or z basis.
Yep.
So that's 3, and there's n qubits, so you do 3 to the n. And so that 3 to the k or 3 to the n looks a little similar. I guess when you want to cover all the possible combinations of 3K local polys, then I think there's some extra factor there if you were trying to just do regular old tomography and look at the sample complexity there. So basically, I'm just trying to compare it to what people might be familiar with coming from that world, and seeing that 3 to the K, which looks a lot like XYZ type of scaling to some power, but obviously the setting is very different here.
No, I think your intuition is absolutely right about where that 3 to the K is coming from. It's exactly that. You are doing, in the end, this Hadamard phasor identity is exactly letting you make measurements in X, Y, or Z bases on each qubit. And you are, for this, it is indeed you're reconstructing expectation values of these K-body strings, knowing the outcome statistically of measurements in the X, Y, or Z basis on each of these qubits.
Mm-hmm. I see, but it's even better, right? I guess, because if I wanted to cover all possible combinations for each, 3 subsegments, like I would need to. There's a lot of them. So yeah, it's better than I think what we. So 3 to the n is covering all the possible polys you could measure. If you wanted k local polys, it would be less than 3 to the n, but it would still scale linearly with n at least. Whereas here you don't have that.
Yes, that's true. Yeah.
So
that's right, because in every entry of the table, you're choosing X, Y, or Z on every qubit. Mm-hmm. So you can use all that matters to use an entry of the table for your particular K-body Pauli is what the Pauli strings are on those K-body qubits. You can use, I don't know if that helped. Basically, you use every entry where you can do any which choice of unitary on the remaining qubits.
Mm-hmm. Is epsilon the additive error on average or is it guaranteed for any K-body string I want? For that string, it's 2 plus minus epsilon, or is it on average the error across all the strings is epsilon?
I think it's guaranteed. So there's the you mean the power here, right? So this is a guaranteed error for the, so okay. This is a guaranteed error on the median of means estimator for any observable. So it's that. And that comes from the usual, at least I understand the epsilon square having to do with the every entry of the table is giving you an independent estimator. So it's the usual beating down the error as the square root of the number of.
Yeah, that looks like the usual scaling or the Chernoff thing, but
exactly. Yeah, I think that is exactly where it comes from. And there you're relying on the fact that you're independently choosing the unitaries on each row. So you're getting independent.
And just to clarify, if you remember off the top of your head, is the statement that if I now pick a particular observable O, then the error epsilon on that particular observable is bounded, with high confidence to this?
Yes.
Okay, so it's for each observable.
Yes. Okay. And there would be front factors here that know about what the observable is.
Yeah, that is the complexity. Good. Thank you. Thanks.
Okay. All right. So, okay. So we're not the first people to think about this, of course, like what happens if you have fundamental conservation laws. So in the original work, this isn't discussed extensively, but it is noted that you could do tomography in this case if you had global unitaries U that you use in this step before you do the measurements. I'll come back to this in a few slides, but this is this it maybe you can anticipate that exponentials in volume or the number of qubits is going to creep in here again, because you're again doing something that's mixing up completely in Hilbert space what different operators you're mapping one operator to really a arbitrary in general linear combination of all possible operators. Kind of other schemes that people have explored, and I apologize, I didn't hear the talk on this from a couple of months ago, so maybe you've heard about even this specific scheme from Sunwon's group. But these are having to do with ancillas and Hamiltonian evolution. So maybe we'll go through this cartoon here. So it says, here is your system of interest within these dashed in this box. And these are empty sites that you have access to. They're ancillas. You do some Hamiltonian evolution of the combined system. And then you stop and you make measurements in the occupation basis on where your atoms are. And the idea is somehow that the measurements of the ancillas applies conditional unitaries on your system, and that you're able to do this and get some kind of effective randomized measurements. Again, I'm not going to talk about this much more. We've analyzed the complexity of these kinds of schemes to the extent possible, and they also scale exponentially in volume. So we're also not efficient. So our work was motivated by trying to find an efficient scheme, right? Which is basically trying to find something as close to that product scheme as we could while being able to reconstruct all observables. And this led us to the all pairs protocol, which I will describe in some detail in what follows. But I just wanted to give you the high level, what does it take and what is it going to give up? So what it's going to take is, I'll build this picture up in a few slides too. So, but what it's going to take is shallow circuits that look like this, which involve two-body gates. Again, there are different choices, but one choice that could work is the square root I swap. This is, hopefully notation people know what that is. It's e to the I pi on 4 swap, or I swap, I think, as well as swaps. So you need these kinds of two-body gates, as well as a phase gate, the one-body gate. So if you have the ability to this discrete gate set, that's what you're drawing these unitaries from. And then you're doing measurements in the occupation basis as before, building up a shadow table that we'll talk about, and able to efficiently reconstruct, again, these classes of observables which have weight k. That's the guarantee that this scheme is going to let you efficiently reconstruct that. So that's the punchline, that this is what it takes and this is what it gives you. So how does it work and why this protocol? So before we get there, let me just one more time tell you again why the product channel didn't work, and that'll lead us down what we need to make it work. So let's just take 2 qubits to be very simple. So we have 2 qubits, 2 one-body gates, and then we will measure in the occupation basis. This is a system with number conservation. That means the number, whatever in the state, in every state of every in row, whatever be the number on site 1 or site 2, you cannot change it because it's acting on each side. And so if we thought about our density matrix that we want to construct, it's a 4x4 matrix. And we're certainly able to reconstruct diagonal entries in this number basis by doing this measurement, right? I mean, for the diagonal entries, the U's don't do anything anyway. So this is just saying that if you looked at your state row, forget doing any unitaries U, and you made measurements in the number basis, with enough measurements, you should be able to reconstruct all the entries of the density matrix that are diagonal in the number basis, because you can reconstruct all possible statistics of number operators. Okay, but there are crucial off-diagonal matrix elements here of the density matrix that actually, are in fact many times things you want to know. So, for example, if these are non-zero here, this could be a Bell state. If they're 0 here, this represents a 50-50 mixture of the 0, 1, and 1, 0 state. And the scheme that you have up here, where you just make measurements in the occupation basis, completely has no access to these off-diagonal elements. You cannot distinguish a highly entangled state like the Bell state from a 50-50 mixture. Okay. So maybe you immediately say, okay, that was because you didn't allow particles to hop between sites. So for example, a Bell state between two sites is a superposition of 0, 1, and 1, 0, right? So you say, okay, if 0, 1 could go into 1, 0 in some way, I might be able to tell. And that's the right intuition. So if we start having, if we thought about pairs of qubits and unitaries that act on those, we can certainly reconstruct diagonal entries. But now we can also reconstruct some off-diagonal entries of our density matrix. So put in the language of these observables, we can reconstruct things like this is a hopping. This tells you the hopping amplitude for a particle to hop from site 2 to 1. So go from here to there. This, and similarly 4 to 3, etc. But again, if you now look, if you've glommed these two up, but if you look between 1 and 3, particles cannot hop between 1 and 3, and we consequently will not be able to get any information of these kinds of observables that are, to measure which you need to allow particles to hop between site 3 and site 1. And so the idea of using these global unitaries or like deep circuits comes exactly from here. It says, look, to reconstruct all observables here, particles need to be able to hop from any site to any other site. Well, we can't accomplish this by just a circuit with low depth, so we need to have a pretty deep circuit. And if you can think, we can talk about how deep is required. But the punchline here is that yes, a deep enough circuit would work, from which you could reconstruct all the entries of your density matrix. But you will, as always, start running into these exponential walls, because doing that channel that it takes, right? So you make these measurements here, and going from here to what rho is will require exponential in volume measurements, as well as resources, classical resources to store all the pieces of information that you're going to use. Okay, so we run back into, this is fine, but this goes back to like the full state tomography troubles that we talked about in the beginning. So what we're proposing is something in between. So it says, how about keeping two-body unitaries, but allowing the two bodies or the two sites to be arbitrary? Okay, so that's what we're calling all pairs tomography. So here's how it goes. The first step is pick a random pairing, the symbol for it is pi, among possible perfect matching. So perfect matchings are basically take your sites, split them into two groups, and draw a line between a site in one of the groups and the other group, right? They are a pair, and do this for everybody. So here's some such pairing telling you, oh no, I guess you probably need the next step to know who has been paired with who. Okay, so but you pick sites, pair them up, and now apply the random 2-qubit unitaries drawn from a specific gate set to every such pair. So yeah, now we can do it properly. So you can kind of see who we've paired up, right? Into each one of these unitaries, 2 lines are coming in, but they're coming in from some, in general, random 2 sites. Okay. And now we measure the occupation basis. And so this is this is the scheme. This is what you need to do over and over again and build the shadow table. So as compared to what we had said before, you have to keep track of one extra piece of information, which is who is paired up with who when you acted this unitary, right? So our circuit topology is changing from one row to the next in the shadow table. And so we have to keep track of that. Okay, so we have that. And as before, this whole protocol defines a channel, which is the expected value of the post-measurement state. But this channel itself, a way to understand it is that it's a sum, with this normalization up front, of the channels for each such pairing or each such circuit topology. And every such circuit topology looks a lot like that product channel that we described before, right? Because yes, it's now acting on pairs, but then for fixed pairing, it looks like there's a unitary for this two, unitary for these two, etc. And this it's a product over those pairs. So we have for every entry of our table looks like the product scheme from before, but when we look across entries, that's no longer true, and this channel depends now on the pairing. And our total channel M is sum over all these pairings. But fine. And then exactly as before, if we can invert this channel, then we're in business because we have an unbiased estimator for observables that we can reconstruct from the state that we have. So each row of the table, undo the unitaries that you did, and then take the expectation value with this funky operator, which is M inverse acting on it. Okay. So what are the properties of this channel, of this protocol? What are the things we can say about it? The first is that actually it's tomographically complete. So this word tomographically complete, it formally means that this channel is invertible, but rather physically what it means is that any observable can be reconstructed from this procedure. Or all elements of the density matrix can be reconstructed from this procedure. Okay, and it's this, as a side comment, this is kind of interesting because it's actually, this is true even though every one of these sub-channels, right, these channels for each pairing are not tomographically complete, they're not invertible. So locality is preserved, right? So we're not completely giving up on the idea that an operator on side I in one of these pairings only gets mixed up with something on side J. It doesn't spread out arbitrarily. So this is where the power of reconstructing K-body observables is going to come from, the fact that we can do it more efficiently. Yeah, and then we're able to apply this M inverse efficiently. Again, this is maybe a comment for experts, how that there's the usual things that help you do this efficiently are missing here. So we don't have a product formula or help from Clifford algebra. Okay, I guess I'll give you a sense for what goes into this. This part's a bit technical, so I'm happy to say more for anybody who's interested, but just think this is mostly a flavor of what's going in there. So the first part is to give you a feeling, a heuristic for completeness, which is giving you a feeling for why do we say from this protocol you will be able to reconstruct any observable expectation value. So consider a particular observable that's charge neutral. So charge neutral meaning this plus operator here raises the number on this side by 1, minus lowers it on this side by 1. So you should have an equal number of pluses and minuses in the string. That means the total number in your system has not changed. That is a charge neutral operator. So here's some such observable, z's on some sides, pluses and minuses. There are 2 pluses, 2 minuses. And this last side is an identity, okay? Now, consider all those rows in the table in which the unitary acted between these 2 sides, the one in pink here, this plus this and that, and this and that, and identity, we'll leave this one be. Okay, so this would clearly be a fraction of the rows in your table because you should have picked this particular pairing for the unitaries to act on. But from all these rows, it's maybe 2 lines to show you that you can use them to reconstruct the expectation value of O, and you can get an unbiased estimator, and you can estimate its expectation value, right? So this is a very inefficient scheme because you're throwing away loads of rows in your table that you could have used to help you with this estimation, but it still tells you that the information to reconstruct it is there in your table. By just choosing the subset from which the reconstruction is very easy, you can show that, yeah, at least you can do it for every such observable. And so that's one way to argue why this is a tomographically complete protocol. But but the scheme that I presented to you here is inefficient. It would need a lot. You would need to build enormous tables if this is how you're going to do it. And so that's the next part of what we did, which is to say, no, we want to use the maximum amount of information for every observable O. We want to use the maximum amount of information from our table to reconstruct its expectation value. And to do that, we had to exploit several symmetries of our channel, and find that the problem of inverting this M inverse reduces to inverting a random walk of the Z operators. I'm going to maybe skip this. And we get a lot of control of this inversion process because our channel has a big symmetry, which is that it's symmetric if you permute all the sites in whatever permutation you apply permutation to the sites. The action of the channel doesn't change, and that's a big simplification, and is why we're actually able to invert this channel. Okay, and I can go back to the slide and say a lot more if anybody's interested. But maybe the takeaway point here is that there's always special features of these channel M that allow people and control over this inversion procedure, and is also underlies why it's efficient. It somehow has to be a simple enough channel for you to invert it efficiently. And here we have that because of this permutation symmetry. So that's maybe the takeaway. This is another symmetry that buys you a lot. So if you can build protocols that have this symmetry, you can likely always build efficient schemes to do tomography. Okay, so I want to give you the punchline table on how does this scheme do as compared to the product channel one, of course, with the caveat that the product channel one doesn't apply, right? So I have the product channel here, but in green, because as is, even though it was very efficient, it does not apply to systems with number conservation. So it's not apples to apples really to compare it with number conservation. All right, nevertheless, so this is our all pairs protocol. How do we do on gate? Okay, so how many gates and measurements do we need? Well, so we need the measurements are easy. We are again measuring each site of your system. There are V such sites, so you need the occupation in all of them. Fine. And in terms of the gates that you need to be able to act on arbitrary pairs of sites, and then the operation that you need to do on each pair is something like a particular beam splitters. So depending on the architecture, this is either you do a bunch of swaps to bring any two sites near each other in your circuit and then act a beam splitter between them, or if you have a natural, if the hardware of your system allows you to move where the sites sit, so for example, there were tweezers that you can move around, then you just bring them next to each other and then you do the beam splitting operation. So the complexity, so yeah, exactly whether it's V or V squared depends on what you have available. But you see here, nevertheless, the number of operations is scaling with V, the number of qubits as a power, and not exponentially with that. Okay, so I guess the name changed here. This used to be called sample complexity. This is the number of entries in your table to reconstruct this an observable to a given error, given precision. And here now it's a little bit more complicated looking. So there is two different scalings, both exponential, but it kind of depends on the number of operators that you have that are the Z type, and the number that are raised that either increase the occupation on a site or decrease the occupation on a site. Those are these N plus operators. So it cares about the character of the operator, whether it's changing the occupation of the site or not, but all of these are still going exponentially with them. And so here there is actually a dependence on the volume of the system and the number of qubits, different from here. There's a polynomial dependence on it. which we think is unavoidable because of this number conservation. Okay, storage, it's very efficient. You simply need to store the circuit topology, the unit trees, and your results. And the post-processing per query, doing this M inverse is also very efficient. Cost, which is scales exponentially with the weight, roughly with the weight of your observable. But then once you pay that one-time cost per row, it's scaling with the number of qubits that you have, which is volume. And there's a specific optimized evaluation scheme that lets us do this. But yeah, again, if you zoned out, the punchline is no exponentials in volume anywhere here, which is why this is classically efficient tomography in these systems with number conservation. I guess I have, a couple minutes more. So we tried this out in a particular physical system to see how good the reconstruction was, but also to get a feeling for, how many measurements do you need for a given error. So we set out to estimate 2 and 4 point functions in a ground state. And upfront, let me tell you, the bottleneck was acquiring the synthetic data from here from exact diagonalization to be able to build the rows of the table, whereas the reconstruction procedure itself is still very efficient for these for the systems that I'm going to show you. Okay, so we took a system that looked like this. So a ladder liquid. So we had these are the 2 rungs of the ladder. Every one of these blue dots is a site of your system where a hardcore boson can live. So we call all the bosons that can on this rung as A and these guys as B rungs. So we allow the hardcore bosons to hop between the rungs, between the on this side, between the A sites, between the B sites, and between A and B as well. That's what this term is saying here. Bosons can hop in all the places we've drawn these black lines. But then they further have an attractive interaction, which is if they sit on the same rung of the ladder, then the 2 bosons that are here and there attract each other. That's this term here. So why this particular choice of Hamiltonian? Because as a function of the strength of this hopping to the strength of this attraction, T on U, this system undergoes a change in properties of its ground state. So it goes from being a paired 1D superfluid, which is to say that when this attraction is very large, then the system tends to form molecules of these on this ladder, and those guys form a superfluid. Versus when you make the attraction very weak, then it just forms independent superfluids of the 2 rungs of the ladder. So that's unpaired. Paired or unpaired is telling you whether you form these molecules or not. So it's so there's something interesting going on in the ground state that we can ask if we're able to reconstruct, and then there are different observables that pick up this or that. So that also lets us ask how we reconstruct those. And so here's some numerical data showing you how we're doing. So the top is an observable that measures that just asks, are you a superfluid? So this is it's really quasi long range order. So there's some details here in 1 dimension, but let me stay. Those are in the statement that I make. When I say superfluid, I mean really with quasi long range order because 1 dimension. Okay, but so this is asking you. This is something that if it's non-zero, as you go deeper into the R is the distance between the 2 operators that we're measuring here, AI dagger AI plus R. This then tells you are a superfluid. If this thing is non-zero, as R gets far away from I, it's telling you you're a paired superfluid. It's a molecular superfluid. So when T on U is small, this is when you've cranked up the attraction. You see that the molecules tend to form a superfluid, but the individual atoms don't, and then they switch when you go the other way. So that's the physics of the system that we're looking for. But let me tell you what's being plotted. So in these faint lines is exact diagonalization data. And our reconstruction of these observables from our all pairs protocol is shown at these data points with these with arrow bars. And this is coming from 10 to the 5 entries of the row, entries of the table. Okay, so that hopefully gives you a feeling of scale. Not an enormous table, but not a very small table. But we're able to, using that, reconstruct interesting observables as well as correlation functions with distance dependence, and also extract order parameters for different phases quantitatively from it. Okay, with that, let me conclude. So to summarize, I've described a local and efficient shadow tomography scheme with number conservation. It's this all pairs protocol. It's a concrete protocol with simple gates, and in terms of its implementation in physical hardware, the reconstruction is tractable because of this permutation symmetry, which I alluded to. Looking ahead, it's easy to generalize this scheme in several axes, other symmetries, double and higher occupancy in each site. To fermions, that's an interesting generalization that we're in the process of doing. There are also some interesting questions of whether this is optimal by some measures. Could you do, we analyzed how our protocol does along these different axes of complexity. But could you do better? Could you have picked a different protocol that does even better in terms of the scaling of the required resources? We don't know. We think parts of the complexity that we have obtained are optimal, but we haven't shown it yet, and so on. I think there's it's a rich field with many open questions. And of course, the most exciting thing in the near term would be if in atomic platforms these protocols are attempted, to see how well they do. With that, let me thank my collaborators one more time, and thank you for your attention, and I'm happy to answer more questions.
Thank you, Anushya, for the very nice presentation. It was a really great introduction. I think it's a staple we can go back to. There's a couple questions from the audience here, and folks, please feel free to post your questions in the comment chat box located on YouTube, somewhere above, below, left or right on your screen. It's the same place where we started off the seminar, so this is a great time to do that, and I'll bring them up to Anushya as we go through here. My first question from the audience: can you give some comments, Anushya, on the optimality of your protocol sample complexity? Is it optimal? Could one do even better, or is this the best that you can hope for using these random techniques?
So with number conservation, right? So I think so. Maybe let me say what I know and what we haven't shown yet. So we think this volume dependence is optimal, and this comes from the fact that there are entries from the table that we're unable to use if you have a operator with which raises the charge on a site and lowers the charge on another site. You can only use those entries of the table in which those two sites are paired by the unitary. That is, the unitary picks those two sites to act on. And so that's where this volume dependence comes from, the fact that you cannot reconstruct anything about that operator from those other entries of the table. So we think that's unavoidable. Now, these exponential scalings is I think we don't know. Yes, yeah, maybe that's the simplest thing. We're not sure. So when you frame the optimality question, you try to frame it. It has to be framed within a class, right? You say it's optimal for given something. And we suspect that if it is optimal, it will be for optimal given depth 1 circuits. So given something that only does, yikes, where is it? Is only given something like this. So which is, we don't think you gain anything from going from pairs to triples to quadruples, etc. But yeah, maybe I don't know the full answer to this.
Good. Thank you very much. Maybe a question from Camus. Can you extend this to computing dynamical 2-point or 4-point correlation quantities?
Yes, I mean, I think we did. So I didn't emphasize that this was a 2-point correlation. That's a 4-point correlation. And we could have done, we did this in the ground state, which is a stationary state, so there's no time. But I think you absolutely, oh, I see. If the question is about, is it about unequal time correlators, maybe?
Camus, feel free to clarify in the comment chat box. I guess there's a follow-up question, which is also from Camus, about how can this method work, or can it be modified, extended easily to states with other discrete or continuous symmetries? So basically generalizing the type of symmetry here.
So I think definitely to other continuous symmetries. I think this, let me see. Yeah, so we haven't talked much about discrete symmetries. I'm sure one can do something like this. I do not know whether it will be optimal, whether it's overkill. But we're definitely to other continuous symmetries like SU2, etc. It can be generalized, and I think as best we can tell, it's going to be efficient. We haven't done the channel inversion in that case explicitly.
Okay, excellent. And folks, feel free to post questions that I missed, because I think that will be a good time now. Question about the errors. So adding these readout gates introduces some additional errors. So the channel by which you're assuming you backpropagate your bit string outcome B, you assume it's unitary, but of course, there's going to be noise, and the deeper the circuit, the more the noise is, the larger it is. So that's going to cause some infidelity. Have you thought about that, how it affects the scheme, and or how to subdue its effect?
Yeah, so maybe one point first is that I don't think so. Absolutely, errors are. We've done the ideal. We've assumed the unitaries that we're acting are ideal, and we have perfect readout in being able to reconstruct, being able to undo the effect of the unitary that you acted. And so not knowing that perfectly would introduce errors. So the first point maybe I wanted to make was that it's not too much worse than what's already been done for the product channel, because there are V single body gates and V readouts, and here there's V readouts, and depending on how you do it, but basically V two body gates. Right. So okay. So we just to say it need not be a deep circuit. It gets a bit deeper if you have to do a bunch of swaps to bring the sites next to each other. But still, in principle, it's not too much deeper than the product one. All right. So that's the first part. So the second is how would it work? So we haven't done a detailed analysis, but so for every such yikes, where to go? Yeah, for every such pairing, this is like a product channel, right? Because as long as you glom up sites, this is a product between the paired sites. So the product channel, these non-idealities have been accounted for in the product channel. So we suspect that it's not worse here, because in every shot it looks like the product channel. Yeah, I don't know if I fully answered the question.
Okay, yeah. I guess the other interesting question is if and how this can be combined with error mitigation techniques, or to that effect. But I'll let sort of folks raise questions. By the way, I should mention, there's some nice comments in the chat you can take a look at after, from Zachary and others, about how they're excited for the very nice presentation and to see more developments in the field like this. And I think folks, seeing as we've had a lot of questions, I don't know if Anushya, you want to share anything else with us before we kind of wrap it up?
No, nothing specific. Thanks so much.
Good. Well, with that, it was a really delightful talk. Thank you very much. I think you'll be one of the ones I'll tell people to go back and watch for, how to get into shadows and understand what they are. Folks, thank you very much for all the questions and tuning in. As you know, this talk will stay recorded on the Skiskid YouTube channel, but the only time you can ask questions live is basically right now, every Friday from noon to 1 p.m. Eastern. So Anusha, thank you, folks. You've been wonderful. And with that, we will see you soon, Friday at noon Eastern on the Quantum Seminar series. To know what's coming up, click like and subscribe.